for you guys to hit play or something before I say anything keepable. All right. It's just past 9 a.m., so let's get started. Welcome, everybody. Welcome to PyCon. Congratulations on being like the very first people at PyCon. When people show up on the latecomers show up for the Thursday morning tutorials or Friday morning, they'll think they're at PyCon, and they won't know that PyCon actually started days before when you guys sat down here with everyone else who supported the tutorial program by getting here early to hit a topic more in depth. My name is Brandon Rhodes. I was, for a while, the head of Python Atlanta. I now live in Ohio and am the head of nothing. And I've been programming in Python and in SQL since, say Python since the mid-90s and SQL since around 2000. And this is the structured query language, SQL, for Python developers. The idea here is to take people who know something about programming, who are already familiar with the idea of strings and lists and dictionaries, and to use that knowledge to teach you the basics of SQL. Some people pronounce it SQL. My databases professor said SQL, so the two camps kind of frown at one another and keep saying it their own way. Whenever I say SQL, I mean SQL. And our goal here is we have 3 hours, I believe split into an hour and a half, followed by a break, everyone to cool down, and then a final hour and a half after the 20-minute break, I think. And in that amount of time, I don't want to rule it out, but I probably won't be able to make you utter experts in what is for many of you a completely new programming language. My goal instead is to do two things. First, as we go, very often when I hit more difficult topics, I will in front of you quickly bring up a web browser and look up the topic in the docs so I can point and say, when you're confused, go here. I don't want to just tell you how something works and not show you how, when I forget, I go back into the docs to learn it. I want you guys to be in the same position I am, where you know how to go get the information you need when you forget the exact syntax of a select statement or something like that. The other goal is to kind of teach you how SQL programmers think. The kind of really, really big picture of how you build solutions with this language. Because you can look syntax up later. You can look up the particular features of databases later. You can do experiments at the SQL command line later, and I hope you all will do that. But what I want to provide you in this 3 hours is an on-the-ground kind of look at, how do I notice warning signs when a query starts running too slowly? How do I think about my data? How do I use SQL in the way it represents data to solve problems? Because what I most want you to go away with is not an utter familiarity with the syntax of the select statement. It takes 5 seconds to look that up on the internet. I want you to know how to think about databases, because once you know what you want to do, the syntax is often the easy part. It's just knowing how solutions are put together that's the difficult part. So to start that process, I'm actually going to begin this tutorial with a fully complex example of how data representation works, because I've been in tutorials and probably run them before where like you start with tiny, tiny little ideas and start building up, and the problem is that no one knows where you're going. They're like, okay, and you make it, math professors. Math professors do this all the time. They are building this little lemma on this other little theorem, on this other theorem, and you're like, what are you doing? Where are you going with this? And they finally get to the conclusion and prove that Taylor polynomials actually converge. And you still have no idea why humanity invented Taylor polynomials, or why it was like one of our top achievements as a species. And so I will start by trying to show you a little picture here of the way data tends to be represented inside of a database. And just for fun, I'll start by not talking about SQL. How about that? I will talk about a popular and fun NoSQL database called MongoDB. How many of you guys have ever heard of MongoDB? Seen it mentioned in blog posts, stuff like that. It lets you store information in a format that looks very much like JavaScript. In fact, it looks very much like JSON, which is a data format where you get JavaScript and take everything out but the data types. You wind up with strings, integers, just like Python, lists with square brackets, and then these things called objects that look kind of like dictionaries, and are they're like Python dictionaries because they're inside of curly braces. But you'll note there don't have to be quotes around the keys, only the strings that are values. And MongoDB lets you, without declaring a schema, without doing anything, it just lets you start throwing at the database records that look like this top one here in order for it to store an index and let you get back to later. And I wanted to put this picture on the screen first because I think to many of us, this is a very natural way to represent the movie Sleuth and its two roles that were featured in the movie, the two characters, and then the actors that played those two characters in 1972. And MongoDB lets you build a database that's actually a very old form of database from the 60s or 70s called hierarchical, where you have a big piece of data, a movie, that inside of it has littler pieces of data, roles, that down inside of them have actors. And this is, if you're hitting data for the first time, a very natural way of doing things. You might have done this in Python before, right? You have a hard problem to solve. You have a loop and another loop and a dictionary with a list inside of it with another dictionary by the time you're done. And this, as I've drawn it here, is obviously going to be an absolute nightmare to try to maintain. I mean, this is just utterly shooting yourself in the foot. And you're going to learn that the first time that you discover you've, say, misspelled Laurence Olivier, because Laurence Olivier was in a lot of movies. And if you've misspelled his name in the actor record inside of the role in every movie Laurence Olivier has ever been in, how easy is it going to be to support like a web text field where you can go in and fix his name? You're going to go wind up rewriting, if I recall, hundreds, maybe it was just dozens, of movies, many of which had like 100 people in them, just to go fix Laurence Olivier's name. So a little reflection on how we really store data in a computer would lead you to use MongoDB more reasonably, as I now have an alternate way down here to represent a movie. And this is more like I'd actually do it if I were using MongoDB. Title of the movie, year, a little list of roles that have names. I mean, that's, if I ever need to fix the name Milo Tyndall, well, it only occurs in the movie Sleuth. Just because I find that Milo Tyndall in Sleuth was spelled differently doesn't mean every movie ever made with an actor, with a role of Milo Tyndall also should be renamed. So it's safe to have this represented once here in the movie. But then, instead of actually having each actor's data in line in the movie record, which both means I have to, it's expensive because I have to store it 100 times if an actor's been in 100 movies, and also difficult to update later, I can just include an integer ID. And then I haven't drawn it here, but over in our list of actors, which we could store elsewhere in MongoDB, we could have them each have a little ID that was easy to look them up by. So if Laurence Olivier has been in a lot of movies, or, oh my gosh, Michael Caine, he's been in like everything, then that Laurence Olivier or Michael Caine, a little integer ID that the database has assigned them, just gets repeated once for every movie they've been in, and if I've misspelled Laurence Olivier, I just can go into that one Laurence Olivier record and fix it up. So we can, some people store data hierarchically, but it's a problem if you need to update it or manage it, and it's also just very large. Down here we have an idea where we're storing it, and this is going to be a key term today, more relationally, where we're using fields to describe the relationship between, say, an actor record and a movie record. But if we're going to be using SQL, we actually break it down one level farther than that because SQL, as a standard, does not support composite values in a field. In SQL, as we'll see, a title can be a string. A year can be an integer. But you cannot have a list of things in a field in SQL. That means that you can't have inside of a movie a list of roles. You can't have inside of an actor a list of movies. And the big takeaway for those of you today who are completely new to SQL, we're about to hit the big takeaway, and much of the rest of the time here for those of you completely new, I'll be introducing more complicated stuff for those of you who've done a little of this before, but for those of you who are new, the big takeaway is going to be, dude, if I can't have lists, if all I have is dictionaries whose keys have to be simple things like strings and integers, what do I do with the fact that there are movies with more than one actor? And this is the answer. This is how SQL asks you to structure data. First, SQL doesn't allow, unlike MongoDB, any loosey-goosey having 100 records, and well, some of them have a name and some don't. And some of them have a year and some don't. In SQL, you declare up front with a statement we'll look at later called create table. You create tables where you predefine with absolute rigidity. You can some databases let you adjust the definition of a table later, but the definition holds true for every row in the table. You define the names and the types of the fields. As we'll see, movie has an integer ID and a string name, and every single row must conform to that schema, period. Here, I have an actor with a random ID that the database assigns, a name and a gender, and every single row must conform, no flexibility. And then, so how do we handle lists? How do we handle the fact that a movie has several actors and an actor plays in several movies? How do we represent data that so often involves lists of stuff if our database doesn't support an explicit list construct? And this is the big deal. This is why humanity invented the relational algebra, because it turns out you can have as many lists as you want if you just create another table and fill it with IDs. Where is the list of actors in Sleuth? You build that list whenever you need it on the fly by looking through the role table, which contains every role ever played in any movie. And you look all the way through these hundreds of thousands or whatever of entries for the ones where the movie ID matches the movie you're interested in. And you can go the other way too. Start with an actor. What roles has the actor been in? And as we'll see, you can actually ask more and more and more complicated questions if the database gives you an efficient way to build the list of answers on the fly by looking for an ID in a table. So We tend to think of data hierarchically as movies, having roles and actors kind of inside of them in our head. If you go to the IMDb page, the movie has actors there on the page. And relational databases, the SQL standard language, makes you break that apart into tables where if you need one thing to be related to a list of another thing, you need to have IDs in one of the tables that take you back to the object represented in the other. So, for the moment, you are free from the mode of tutorial where I stand and talk, and you, the victims, have to sit and listen. And we're going to rock back and forth between those two formats this morning. Do all of you guys have your first steps SQL tutorial exercises handout? We're going to start now flipping occasionally into you guys get to go and experiment and explore mode by one at a time kind of throwing you at these exercises. You'll be working on them, and then I'll jump in and teach you some more, then you'll work on some more, and we'll start slowly iterating through these to show you how we build lists, answer questions, and build interesting relationships when all we have are tables like these. And in fact, these are very much like the tables that you guys have access to. How many of you guys were able to go through the install instructions in the email and have the SQLite and command line and the movies.db database? And what I'm going to do is, as I get all of the guys whose hands were just raised started on section 1 here, I have a key fob over here on which I will put one or two copies of the database, and I will just walk around right now to those of you who don't have it and help. And this was supposed to be the TA's job. He will owe me a beer later. And get you guys up and running with those of you guys. I will get you guys running on being able to look at the database as well. But first, before throwing you into this first section, I should show you something about the select statement. I'm going to do two things. I'm going to open up a web browser, and I invite you guys to do the same and look up SQLite 3, which is the database that we're using. For those of you guys who haven't seen it before, one of the neat things about SQLite 3 is that the database is a single, simple file. Most databases, most SQL databases, when you start them up, need like a special area of your hard disk, and they start creating directories and files, and it's all of this stuff. SQLite 3 is kind of it's a brilliant concept. It's a minimalist SQL database where the whole database just lives inside of a single file. It's great for things like this tutorial. It's great when an application needs a little SQL database. But have any of you guys ever installed a product at work or something where step one was go get an Oracle license and set up an Oracle database? Oh, okay. Yeah, okay, thank you. It's really horrible when step one is go buy and set up something like Oracle. SQLite, I don't know if you guys know this, but I believe it's Firefox, keeps a lot of your user settings and its cache database in a SQLite database, but you've never had to worry about that because Firefox just comes with the SQLite library built in and is able to all the time have little single file databases under your Firefox settings directory, and you don't even know it's there. It's really incredible that a lightweight tool like this exists. If you look up, in this case, SQLite 3 statements, go to the query language understood by SQLite, and we will go to, down under S, the select statement. Every database has its own page on understanding each of the basic SQL statements. For example, another database that I will mention today called PostgreSQL I can look up PostgreSQL, select statement, and actually Google brings up, they have several versions of their docs. I'll click on the 8.2 version. This is how the immensely powerful PostgreSQL database explains the select statement. And I don't know, that's a lot of information. And on the one hand, it's awesome all the stuff you can do with select under PostgreSQL, but I often find the SQLite approach to be just a lot more fun. It has a little diagram of how I can put select statements together. And I often find these really, really pretty little diagrams a lot easier to understand than the most other database documentation, which tends to use this more lexer, parser-based approach to defining this language. But at the moment, we're just going to look at the idea of what they call a select core, a select statement, maybe with a little limit thrown in, as I'll show you in a second. So the thing that you'll do in order to tackle this first group of questions is you'll go to the directory where you have your movie.db file. You will run SQLite 3 on movie.db, and you've now opened the database for exploring, for reading, for writing. And here are the things that I tend to do when I connect to a database, because I always forget what's there when I come back a month later and I'm like, oh, I need to add something to that database. SQLite 3 lets you see live the tables that are defined in a database by typing .tables. And it will list for you the names of the tables to kind of remind you what's there in the database. If you type I believe it's schema, followed by the name of a table, it will show you what each row of that table must look like. And brilliantly, it does so by showing you the create table statement that you would use if you were creating this table in a database that didn't have it. And by the way, I really like this. Some SQL databases, of course, all of them make you use the syntax to create a table. But a lot of them, if you look back later and say, I have forgotten what was in the movie table. Could you show me? It uses some other output format. So you have to learn both the way they picture a table once it's created, and then you have to remember the different syntax for creating the table at the command line on your own. And I love that when SQLite wants to show you how to create, when you want to say, what's the format of that table again? They just echo back for you exactly the command you would use to create it from the ground up. If you look at these tables, role, a movie ID, an actor ID, and a name, look essentially like I promised you in our little example diagram, which maybe I'll keep up while you work. If I ask for the schema of the movie table, we find that there were a few fields I couldn't fit on my slide, like there's an nth field because sometimes there are, in fact, several movies of the same name released in the same year. So IMDb gives them the Roman numerals 1, 2, 3, and so forth. There's a variable that's true or false that indicates whether it was just one of those like horrible movies they just released directly to video, or whether it was like actually shown in theaters. And if we look at actor, it looks like I got all the fields into the slide: an ID, a name, and a gender, which in this case I just had as a string M or F. So the two ways to sort of explore a database are to use the database's secret commands. This isn't standard SQL. That's why the dot tables and dot schema begin with a dot. No valid SQL statement begins with a dot. So SQLite threw these in because it can tell when you start with a dot that you're not trying to type a SQL statement. So it can take over and say, oh, let's show him what the tables look like. And by the way, just schema with no argument shows all of the tables definitions, if that makes is a faster refresher for your memory than asking for them each individually. That's actually one of my most fun ways when I connect to a database to kind of remember what's there, see the lay of the land, and see how the data is being stored, is to use the dot commands on SQLite. I might show you later the PostgreSQL, the way because SQL commands also can't start with a backslash. If you're connected to the PostgreSQL pSQL prompt, this is how you would list the tables. Backslash, show me the data about tables. I think that's an abbreviation for a bit more obscure. But in general, most databases, even though standard SQL doesn't give you a way to see what tables are there, all database authors recognize that that's a pretty common operation for us. So they provide some out, like these little dot prefixed commands for exploring what's in the database if we weren't the ones that created it, or if we did but have lost the source code and can't get back to our create table statements because we've forgotten them. The other thing I tend to do when exploring, and this is standard, this does work everywhere, is using, and here you're seeing your first select statement, those of you who are completely new. Select is the most frequently used SQL command. It asks to see some rows from a table. When you're just exploring, you tend to just say, select all of the columns from the table, let's do movie. And now the problem is, if I hit enter, my computer will almost become unresponsive as it tries to render pretty anti-aliased terminal font for the thousands of movies that start scrolling past. So as I said a moment ago when we looked at the syntax, there's I'll teach you right off that there's a little, what's it called, qualifier you can add. This is the most basic form of the select statement. Select everything from a table. But there's another qualifier you can add that says, just show me the first 3 rows that come up, or where you can put any integer there. And the fun of that is whether I do 3 or 12 or however many, it lets me kind of start to see what's in this database. SQLite and in PostgreSQL, it shows you the titles of the columns, which is really helpful. Here in SQLite, you'll want to say mode, I believe it's mode column will, and then let me limit this, breaks it into columns rather than using those pipe characters, which might make it a little easier for you to read. The pipe characters, which I believe the default mode, I think is called mode tickle. The pipe characters are kind of cool because you can see whether there's extra white space around your strings. If you've accidentally ended a movie name with a space, that can prevent it from matching, where you say, movie title equals foo doesn't work if the actual title has a space in it. So while having these really literal modes that show you exactly the characters and then break it off and go on to the next field are helpful, I, again, normally in SQLite like column mode because it just looks more like the columns in tutorial leaders' slides. Yes, sir? And that means that I was utterly incorrect, that the default mode must not be tickle mode. In the interest of time, I will explore that question once I have you guys working on the exercise, and I'll remember what the name of that default mode is. I don't remember. The other thing you'll probably want to do is turn headers on, and once you've said .header on, this pretty text format it's using to show you the data you get back puts the field names up at the top. Because, again, normally what I'm doing when I just select star from table limit 3 is I just want to kind of see what are the fields, what do they look like, what kind of values do they have in them. And this is a neat way to explore a database and just take a quick glance at every table because it's universal. I don't have to remember what is SQLite's way to list the tables that exist and what is PostgreSQL's way, and I don't even know what the people do who use Oracle. select all from table name limit 5 or 3 or whatever works on every database. So the one thing I believe that you will need to know in order to tackle the first group of exercises, and let me go into my list of the exercises here, is let me show you a few operators. First, with select, as you've seen, you can just try to select the whole table, or you can limit yourself to a few rows. You can, if you want, just select one field, like limit 3. You can just select the title, or just select the year, or by separating them by commas, select some little list of columns instead of every single column in the database. And then finally, you can, if you don't want every single column, you can use another qualifier, and here I'll remove the limit because now you can use both of them, but I'm going to use where to limit the movies that come back. You can say where and put here some condition. The most basic kind of condition, I hit enter by accident, is testing a field for equivalence. Select title and year from movie where title is empty. Didn't come up with any rows. It happens that no movie has ever had the empty string as a name. Curious fact you might not have learned from IMDb. But if I say where title equals Batman, now it's coming up with all 4 of the Batman movies with the simple name Batman that have ever been produced. You can, if you want to what if we wanted all movies that have Batman anywhere in their name? There's something called like, where the percent becomes kind of a wild card character. So this, select title and year, from movie, where title is like, percent means anything, followed, it's case insensitive, I believe. We'll find out in a moment. Batman, followed by anything. If I do this, then we find that there have been quite a few movies through history that have had the word Batman. For instance, the 2003 I Hate Living With You Batman, which I'd never heard of until this moment.
Star Trek versus Batman.
I don't know. Interestingly enough, and then if you want to, so in addition to equals, you can do greater than or equal than, and you can use and or to combine things. So I can say where title like Batman and year is greater than 2000. And this is just the Batman movies and or TV episodes that have, or just the movies and videos that have been since 2000. What if we ask for everything /2010? That's a lot of stuff. I think most of these are animated shorts, if you're wondering why you didn't see all of these in the theater. But they all get entered into the movie database. So this is the basic syntax of a select statement. And again, the operators you can use and or to combine larger questions. Less than, greater than, equals, and I actually like using that old-fashioned SQL syntax down there. Greater than, less than means not equal, either greater than or less than. Notice that the equal sign is not a double equals as in Python, but a single equal sign. And then you can also say like, pattern and have percent statements after it if you want to do some comparisons. Note that the strings are quoted by single quotes in SQL. You'll remember that Python lets you just willy-nilly use single or double quotes, but SQL makes you use single quotes. And one last thing, sometimes if we go back to that select statement, where we were just looking for everything with Batman anywhere in the title, and it's just a lot of results. You can also just say this, which we'll look at more later. If you don't want to see the huge list and have it scroll off of your screen, but that you instead want to just get a count of the matching rows instead of seeing the rows themselves. So I believe that with these tools, you guys can now get started on learning the select statement part 1. For some of you guys, these will be really simple. Feel free to jump ahead to to just keep going and experiment with the further exercises if you've touched SQL before. But for a lot of you guys, answering these first 5 questions under section 1 is going to be your first experiment. And don't worry if you get syntax errors and stuff like that. I'll be walking around and helping out. But given these few examples I've shown you of select statements, see how many of the 5, A, B, C, and D, you can answer using a simple select statement, either with count or that grabs all of the fields, a select statement of the form that I've shown here. And I will walk around and start giving people copies of the database. Introduce the, sorry for not signaling you earlier. I'm now going to quickly, so how many of you guys have gotten through a few of those first few queries? Have those worked for anyone? Let me quickly, so that we all are on the same page, let me quickly suggest how I might solve 1 or 2 of them. In what year was Double Indemnity released? And sorry for the flash on the screen. If you look here on the screen, the way that I would solve that problem, and by the way, SQL is case insensitive. Once you're inside of quotation marks, of course, case is sensitive because it's got to either store the capitals or lowercase or whatever you type to the database, but its own table names, column names, and keywords are case insensitive. You can capitalize them however you want. The convention, believe it or not, this is I think a 1970s language in its origin, is to capitalize the keywords and to leave your own stuff, your tables, your columns, lowercase. It looks really weird, but it's what you'll often see in SQL books. So I'll be using that a bit today, just so that you guys kind of get used to how that looks. But the simplest way, I think, to answer question 1A is just to select year, that column, from table movie, where the title is the movie title you're looking for. And it turns out that that movie came out in 1944. The second question was similarly simple, except that instead of needing a piece of information, you needed a count. Because, of course, as we saw, if you don't do count, you just get all the answers sprayed onto your screen faster than you can read them. So one way of answering 1B would be to say, well, all right, 1929 saw more than 2,000 movies made, but that, of course, was the year of the great stock market crash. And the next year, only 1,800 were made. Hollywood saw about a 10% drop in the number of movies made as the financial disaster took hold of the country. And that only went up a bit in 1931. So that's where you can see an interesting blip in film history where a nearly devastated economy hurt Hollywood by 10%. It's interesting how well insulated they are from the rest of the world. People were starving, and Hollywood had to make 10% less films. Partly because actually films became a big escapist kind of phenomenon. I'm told that the whole kind of film made in the 30s tended to be much more escapist, much more, I guess I won't finish this tutorial if I keep going on to film history every time I hit a question. So forget what I was just saying. How many movies have been released to theaters and how many were instead released direct to video? If you did, again, just a little exploratory select from movie, you would see that for video is either a 1 or a 0 in the first three that come up. It happens to be 0. But it turns out that the easiest way I found to answer this question is to select the number of movies ever made that actually went to the big screen, and then to select the number that went straight to video. And despite the fact that you might feel that the world is absolutely flooded by horrible, B-level, cable quality, direct-to-video movies, it in fact turns out that they do not yet outnumber, by a huge margin, they don't outnumber the number of legitimate horrible films made. Movies, when I ask the question about I'm sorry, I didn't mean to move that window. The number of movies with yoga in their title, when I said, what about movies with yoga in the title, asking how many were released straight to video and how many were released to the theaters, the idea was for you to get a little practice using and. How many movies have a title like blah, 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 yoga, blah, blah, blah? And first, how many times has a real movie been released to theaters that has yoga in the name? 43 times. If I replace count with a title, we can ask, what were these movies and how did I miss them? Yoga Man. I never saw that. Yoga Incorporated. I never saw it, etc. And then by saying and for video equals 1, we can answer the second part of the question that 87 direct-to-video titles have had yoga in the name. Thus, we see that yoga movies reverse the normal trend. Even though far more movies have gone to the theater than went direct-to-video, the opposite is the case for yoga videos. They, by I guess a 2-to-1 margin, tend to be designed for video rather than for release in theaters. And then the little Venn diagram to show how often the words life and death appear in films is similar, where you can do, and I'll just, paste them in one at a time. Select a count of the movies where title has life and title has death. 84 movies have managed to get both life and death into the title. 1,200 movies managed to have not the word life, but the word death. And, I should have shown you not like. And 3,000 movies show you the word, have life, but not the word death. So if you had a sketched on your page, you would be able to draw the circles and the overlap with those three numbers inside of them. Oh, I forgot that that's the second line of a two-part query. The answer is no. They're exactly the same. Yes, that's correct. I was thinking of an obscure edge case, but even in the obscure edge case that we'll talk about later, they're the same. And again, I encourage you to be looking at this SQLite language core to kind of get a glimpse of the different ways that these conditions can be put together. To get you ready now, let's just keep going through the different sections where I'll give you a minute to try some of them out, and then I'll give you the example queries that I use to answer the questions. For section number 2, putting things well in order, the next big part of the select statement I'll show you is order by. Order by, which comes after the where clause, but before the limit, if you choose to use one, is designed to ask for the rows, which, as you've seen, tend to come back in just kind of a crazy random order. Order by tells the database to go ahead and take the time to put the rows in some particular order. And if you, again, look at your syntax here on the SQLite page, you will see that the syntax of it is order by, and then what they call an ordering term, which if you scroll down a little bit, can either simply be an expression like year for a movie or name for an actor. Ignore the collate keyword, but you might want to use ascending and descending. That tells it to order with either A through Z, or descending, where it starts with the Z's and goes through the A's. SQL can order either strings or integer data. So the first question, for example, what was the year that the very first movies were released? The way that I would answer that is simply this. Select star from movies. Oh, and I guess given my screen size, I should do fewer rows. Because I bumped up the font right before giving the tutorial because I figured you'd be able to see it better. Select star from movie, and instead of just letting it print all movies out, I said order by year ascending, so it starts in the 1800s and goes to today, and then I used that keyword limit 5, and this is a very, very important relationship. We saw before that limit just kind of got the first rows, and they were just whatever random rows happened to be first in the database, and only showed us those. If you combine limit with order by, you get something very powerful. You get the ability to ask the database to sort by a field, but then only see the first few. This is often how a web page will show you the first 25 results without taking maybe the several minutes to pull all million results or whatever from the database. The ability to say order by a field, ascending or descending, and then stop once you've given me 5, instead of transmitting back to me all, or even computing, all of the rows that would answer the query. So go on now. I'll go offline for a minute and walk around to help people. Go through the other queries in putting things well in order. I will mention one other operator that you will need for a few of these queries, which is you can ask about the length of something. And you can use this over in your fields that you select or over in an order by term you can use length to get the length of a string. So here I'm selecting the length of title from movie, limit 3 so it doesn't run off the screen. Now, instead of just printing the titles, which you'll recall, those are the first 3 titles that happen to come out of the database for me, it's now doing their length. So if I wanted to get the roles with the longest names, I could say select name from role, order by length of name, and then limit to some reasonable number. I think you'll find that helpful as you go through section 2. Go for it and see how many you can answer. I'll give you a minute or two. Let me show you. By the way, since I understand that going to the SQLite documentation might be a little annoying every time that you need to remember a syntax, I'm starting to compile just a list of kind of examples to remind you if you're having problems with the syntax of the different ways that you can compare different expressions and values. Hope that is helpful. Let me now throw something else into the mix. For our third group of questions, making distinctions, there's only one new feature you need in order to tackle those. Using the keyword distinct, means that the database gets the list of rows that it otherwise would have given you and eliminates all duplicates so that as they print out, you will never get two that are the same. It collapses all the ones that are similar together into a single row. And so I think that if you'll, if those of you who are ready, go ahead to section 3, I think you'll find that that's helpful for answering those 3. I'll give you a minute to try some of those, and then I'll show you a few of, we'll talk about a few solutions to sections 2 and 3. To discuss a few of the solutions you guys have discovered, I'll just pick 2 or 3. How did you guys do 2B? What movie has the longest title ever? Who has like has a suggested solution for that? Was the length of the title? What was the select statement that you did? Let's try it out so everyone can see it here on the screen. I'll type it as you.
Select length in parentheses title from movie order by length in parentheses title. This DESC for descending limit 5.
And it churns over the movie database and comes back very good with 239 as the longest movie title ever. I'm going to do 2 things to the query. Watch this. I'm going... What was the question that I asked?
What movie has the longest title ever? You're saying the movie 239.
And thus I am going to add to the query a second field. So, all right, according to the wording of the question, we were supposed to actually identify the movie. So watch, everyone, what I'm going to do here. I am going to select 2 columns, one of which is the length of the title. I'm going to put it at the left so it'll stop bouncing around as the titles are long and short. And then the title from each movie, order by length title, and that can churn and give us an answer. And actually, let me do this. It turns out, I hadn't told you this, but in order by, if you don't want to repeat, if the thing you want to order by happens to be an expression you're also having returned to you, you can just name that field number. So here, because, if I did this, if I said select title from movie, order by length title, then that's sort of the simplest possible way to get the answer. These are so long that I am going to limit 2. That is the longest movie title ever. The Prince of Wales decorating the Monument of Champagne and receiving address of welcome from the Mayor of Quebec, etc. This is from, I believe, if we add title and year to this output of movies, I'm sorry, that's 2 movies, and I wasn't able to see clearly because I didn't have the years to visually break them up. This is a movie from 1913 and 1908, back when movies tended to be just 30-second little shorts of some important historical event. Back then, they actually fully described the event, and I guess because they didn't have IMDb, they just included the actors right in the title of the movie, I guess, to make things easier. But notice the form. Notice that I'm ordering, in this case, by something that doesn't even appear in the fields that I'm selecting. But if I do happen to, you'll note that the way I did the select didn't actually tell me the length. I would have to go count character by character. If I actually want to see the length, I have to do exactly what you suggested. I have to have length title in the columns that are being returned to me. And in that case, only if I want, I can abbreviate the order by clause by giving the integer number, 1, 2, 3, 4, or whatever, of the column of output that I want it to be sorted by. And notice that makes sense. You would never want to sort by the constant integer 1 because 1 is the same value for every row of your database, so to speak. It wouldn't impose an order. So it's a shortcut that the SQL language offers us. And so this query, select length of title, title, and year for movies, ordering by the first field, gives us all of the information of all of the previous select statements I was doing in a single output, where we get both the title and the information that it was a 239 character title. Once again, you can see that they simply listed the cast in line in the title. So then something similar was possible for selecting an actor or actress. Raise your hand. Did any of you guys get curious and actually see the names of those actors come past your screen? Could one of you guys tell us what were some of the 1 or 2 or 3 longest names ever used by an actor in Hollywood? Anyone? Yeah.
Most of the names were groups of individuals.
Were corporate actors that were not were a corporate body of people that were an actor. Does anyone have one example still on their screen or that they can scroll to? Yeah.
Man of battle company of second of the 503rd Infantry Regiment, 173rd Airborne Brigade Combat Team,
Comma the. And I can just, I almost want to go see that movie to see how did they format that on the credit screen. It probably like needed its own thing scrolling by just to see that. I'll skip over D, but that was, the idea of that was to just get you to practice using like. Were any of you guys amused as I was to see that the very last movies in the alphabet are, from what I could tell, ZZ Top movies? Did anyone get a solution for 2E that what were the and this was the idea here was to do an order by, but pay attention to the second 20 results. Did any of you guys get a select statement that you liked for 2E? Yes, sir.
Limit 11, 10. At the end, so select title from movie,
And I'll just throw this in because it helps orient me.
where title, like parenthesis, quote, percent, gun, percent, quote, limit 11, 10.
And so you used a really cool operator that you probably either knew about already or saw about in the documentation. So the easiest way that I thought some of you guys might do this was just to say limit 20, and then, but wait a minute, this is showing me just random movies from random years from what I can see. 2013, which hasn't even happened yet, 1947. I think that there's one more clause I'll throw in, because I said in the order in which they were released, so watch this. We just need to go in and add one little thing, order by year. So we're selecting title and year for movie, where title has gun in the name, order by year, so it's not just a random assemblage of movies. Limit, and if you say limit 20, then you can look at the bottom 10 here and see that, my gosh, movies about guns started coming thick and fast in 1912. What happened in maybe they developed, I guess that was probably when they invented movie blanks or something, and they're like, finally, we can make a lot of movies about guns. But it's sort of interesting that, like, back in the early days of movies, the innocence of Hollywood, like all of the movies have guns in their name. So you can, and what I expected was just do a limit 20 and look at the bottom, the second 10 that show up. But there are two other alternatives. The more canonical one I've seen before, which is the one I'll interest you to, is limit 10, in this case offset 10. Limit, as you've seen it so far, shows the first in rows. Offset skips the offset number of rows and then shows you limit rows. So doing this by itself skips the first 10 films ever made with gun in their title, and instead shows you, did I really do what I just think I did? Or did I cut all of the titles down to 10 characters? Why did it cut? I've never seen that before.
You have order by year, but then you don't have ascending, descending.
Let me, so order is ascending by default, but you're correct that specifying it can always help keep up with that. So thank you. I've thrown in year ascending. Okay, I'll go back to the default. All right, so interesting. The column format that I was used had been showing me full movie titles and then suddenly decided not to. So I don't know if that's a bug in SQLite or something I hadn't encountered with its column mode. Now I'm back in mode list, which is kind of ugly. You know, it lets the subsequent columns flow left and right depending on how long the first column is. Uses a pipe character to limit it, but we now have the full titles back, such as The Adventures of Dick Turpin, the Gunpowder Plot from 1912. This combination, limit and offset, is very, very important when building web searches. Limit and offset is what you'll typically use if you have a web page that shows the first 20 results and then a next button, and then that second page of results has a next button that takes you to page 3. What's actually happening there, and I'll do it here with more like, limit 3, is the first page of results will just say limit X. And we get 3 movies. We can then say, for the second page of results, limit 3 but skip the 3 we've already shown. And we get another page of results. We've now shown the first 6, so page 3 needs to skip 6, the next needs to skip 9, and in general, the formula on the web for showing the nth page of results is to show page 1 of results without an offset, and then to show the subsequent pages with essentially, I guess, n-1, because that's the number of pages you've passed. So the page number -1 times the number of results per page, so that you do offset 20, 40, 60, 80, getting deeper and deeper into your database's result set as you go. Let's look at 1 or 2 solutions for section 3. How many of you guys had an answer for 3A, creating a query that just outputs the 2, or I guess I did that on the screen. I'm sorry, I won't ask you guys to repeat that back, since I think that that's what I put on the screen as the example of select distinct. But here's it's reading through the entire actor table and is only noting unique values that it comes across. So even though the actor table select gender is MMF, MFF, MFF, all of the genders in whatever order, it's coming out with just the 2 unique values. It's collapsed all of the Fs together and all of the Ms together. Yeah? If you say, and so this is going to, I'm going to give the honest answer to this question, but it will involve a concept that we will start talking about at the beginning of the second half. But everyone listen. If I say select star order by 3, it just grabs the first 3 rows that happen to be in RAM or are easiest to get to or right at the beginning and end. There's no limit on how easy the database can make life on itself, and it displays whatever 3 rows it can get most quickly and does not touch the rest of the table, because you don't need to look at the whole table to return 3 rows. If you say order by something return 3, and there's no index on the table, no way for it to quickly jump to the few first or last values, then it will read the entire table just to return those 3 rows. Because the row that's first in order might happen to be at the very end of the table on the disk. So it's just going to have to read the entire table in from disk, because until it's read it to the end, it doesn't know that the 3 best it's seen so far aren't going to be trumped by something even earlier in the alphabet that it runs into later. If, however, there is an index that exists on the table, then it will use the index to jump immediately to those 3 rows and only select those from the database. So, as we'll see, almost everything with a database is going to be too slow for production unless you have an index speeding up the web search the person's doing or whatever else. The next construct, in which years in human history have there been at least one movie released? That's simply to select distinct year from movie, so it collapses all of the years from 1984 together into just the single year 1984. By scrolling to the top, you can see that film was invented in 1888. There are like 3 or 4, I think, few-second movies from that. You can watch them on YouTube. Movies from that year that are the very first movies in the IMDb, the Internet Movie Database. And then finally, for a little more fun, I said, produce a list of role names where your list only has each role listed once, which start with the word bystander. So what I want to do is select name from role, where the name is like bystander blah. Because I said start with the word bystander. Notice I therefore omitted that first percent. Because percent just stands for any string, percents on both ends would allow bystander to be anywhere in the role's name. But by eliminating that first percent, it has to start with bystander. There can't be any characters to the left of that, but it's allowed to end with anything. We run it, and we will see all of the different kinds of bystander that Hollywood supports, including bystander, bystander number 1, bystander number 2, bystander outside church, bystander at harpsichord concerto. Yes? Yeah. Year? You did select distinct year from movie? That might be a difference in our versions of SQLite. My version of SQLite, and maybe during the break or right after it'd be interesting to look at that. All the versions of, so let's first say, this has no order by. The database is, according to the SQL standard, free to do what it just did to both of your days, which is to give you a completely unordered response that in this case isn't very useful to you. It's free to do that unless, and exactly as you just said, order by year is the thing that makes sure that those come back in the right order. I think the issue here is that my version of SQLite does distinct by ordering them and collapsing them together. It just happens to order them in RAM as it's reading all the movies ever made. It's just sticking into an ordered list the years that it finds. So its implementation of distinct happened as a side effect to order them, but you're correct that without the order by, the database is not being asked to order them. It just happened to do it with the SQLite version that I'm using. Okay, and so then I also showed how to do the bystanders. I'm going to, now you've seen before, I'm going to introduce one more concept. We'll play with it for a minute, and then we'll go to the break. The idea of a group by. And we're now getting complicated enough that I actually have kind of a little picture here that I tried to draw of the order in which select does its operations, where you have a table with all the rows that you've added to the table. The where clause grabs those. Group by, which we're about to see, asks for those rows to be clumped together according to some field or criteria. There is then going to be something exactly like where, but called having, that operates on the results of the group by, and then order by is the last thing that happens before it returns. And the way that you use it is something like this. You noted that we had this really cool thing called count, which shows us how many rows are in a given table, 1.7 million in this case. But if we wanted to know, like, how many actors are men and how many actors are women, we have to do two, so from a technology we've seen so far, different queries. We have to ask for gender M, go through the whole table, and then gender F. So far, the ways we've seen of getting M and F back in the same query don't give us a chance to run count. And the answer here is to do a group by, because count, which up until now we've been treating as though the count operation, as though it simply counts the number of rows being returned, period. In fact, that is not its definition. Count tells you how many rows are in each group that gets returned. And it just so happens that without group by, you only get one group returned. All of the queries you guys have done so far today return to you one group of results. And if you had a count in there, it counted them for you. But with group by, we're able to do something like this. This is kind of the canonical way group by works. We can either do this, select count and gender from actor, where we group by gender before throwing that result at count, that set of rows at count, or group by allows you to do the same thing as order by, and if you just don't want to repeat it, you can just name the column you're creating that the answer should be grouped by. So again, and let's go back to the ugly picture I drew, ugly but hopefully helpful. What you should see here are the maybe all of the M rows being pulled out of this where result to here, all of the F rows being pulled to here, and then the aggregate function you're calling, like count. An aggregate function is something that just gets a big bunch of values and makes them a single value. That is being used to create a single row for M and a single row for F. And so I believe the query has now had time to complete. You see that here we're able to answer the question of how many actors and actresses have there ever been by counting, but by grouping by gender, so that all of the M rows and all of the F rows are together, and then having a count included so that all of the M rows get collapsed into a single row with the count and the M, and all of the F rows get collapsed together to a count and the letter F. Let's see. Now, there are several aggregate functions in SQL. If you look up SQLite 3 aggregate functions, it'll bring up a page that has a lot of them. But count simply goes through and tells you how many values there are in, amongst all of the rows that you've pulled back. There's also one which is more useful for if you're doing a numeric field called sum. And there might also be one called average. Let me do something silly here, but that if it works, we'll illustrate it. Select average of year from movie. Well, that worked well. Great. So, and notice, just like count, You can use this aggregate function in a normal query, in which case there's one group and your whole result set gets collapsed to a single row, or you could do group by in order to try to pull together different groups that each got their average computed. This is kind of interesting. The average year in which any movie was made is 1980. That means it took 1880 to 1980, the first 10 decades of movie making, to make half of the world's movies, and we've done the other half in the last 30 years. I guess that means the rate at which we are making movies is increasing. Neat. Anyway, I think that should let you guys get started on Section 4. Try one or two of the things in Section 4, and then I believe, is it now break time for them to go get a 10 or 15 or 20-minute snack?
That's 10:34.
You had a question.
Several groups that you wanted to group together, some or count or whatever, you have 4 or 5 groups, and you just want to return one. Can you pick which group basically it returns instead of saying return all the groups or return the first group?
You would simply combine, I believe you would simply combine this with a where clause, limiting the set of rows considered to only the ones that were going to go into the group that you were interested in. Or you could, or if you wanted to have it compute all the aggregate rows, but then only pick out a few of them, you could use having, which, again, it's just like where, but it occurs after the group by. So let's say that you were doing groups that counted up some average. Let's say that you were looking at departments at your workplace and computing people's blood pressure. And so you came out with IT department 115, management 185, and because they're all going to have heart attacks, and we're going down, but you actually only wanted the departments that had high stress levels so that you could do some intervention. What you could do is you could say, and I'm going to completely make this up on the spur of the moment, so forgive me if it's nonsense, but I think you would say, blood pressure. Systole is the top number, and diastole, I think, is the second. And I've misspelled it, but what the heck. You would do something like this, from Department Health Stats. And there's two things you could do here. So you need, note that, and this brings up an interesting question. What do you do when you want to refer to a synthetic value you've come up with? Because we want the rows that have this average blood pressure, let's say above 120. What we can do is SQL, and here I'll turn the keywords capitalized just so that we are clear here, which of these symbols are ones I'm making up and which ones are real SQL. What we can do is we can give an arbitrary name that we just invent to any of the columns that come back from our database. So I can say select the average blood pressure as average BP, can just be a quick throwaway name, from Department Health Stats, and now that it has a name, I can say this. And so this is what you do if you are, and we'll see a little of this if we make it to Section 6. This is a little bit of what you do when you get a bunch of results, collate them together into groups, compute a sum or an average or some other combined value for each of those groups, and then just want to throw some of the groups away because you're not interested in the healthy departments. You're in charge of the insurance, and you need to go help out the departments that have high blood pressure. And so note here that when I did the little diagram of where, group by, having, order by, that is the exact same order, as you must use those qualifiers in your select statement. This is a really cool feature of the select statement. The syntax itself and the fact that you must do select columns from table where, group by, having, order by, and then I guess I should note for completeness that limit and offset are then select some smaller list of the fields, the rows that are coming back anyway. The fact that the syntax forces that order means that the statement and the way you've written it always matches exactly the order in which the database is going to apply operations. This kind of picture that you need to have in your head when writing very complicated select statements is the exact same order that you'll use when you're looking at the syntax and of the select statement and typing all of those qualifiers in order. Was there another question before we break? Yes, sir.
I don't quite see in the example that we talked about with blood pressure where the difference is between a where and a having. The idea is we're saying having a blood pressure greater than 120 versus using the keyword where.
And so what I'm going to do is I'm going to, through the ugly expedient of adding a lot of spaces, I'm going to put this, I'm going to write the query that you just suggested, and then through the expedient of having a lot more spaces, I'm going to put it high enough on the screen that you guys can see it. Wouldn't it be useful if we had a language and a civilization where stuff scrolled downward, since it's always the top of the screen that's easiest to see in presentations? I should suggest that to the civilization people. The first thing to observe is that this is impossible. I can't do a where on average blood pressure because it doesn't exist in the where stage. In the where stage, I only have literal rows from the table available. I don't yet have any of my aggregate fields computed because this average takes place after the where and before the having. So the way I would have to write this is like this. If I wanted to apply a where clause to this clause, I would have to use the literal blood pressure of each employee and throw out the employees whose blood pressure was less than 120. So if I do a where on blood pressure, it's talking about employees. If I do a having, it's talking about the averages of whole departments. So let's be clear about the difference, because they each do something that might be useful. The first select statement that I wrote says, let's get every employee in a department, compute using those employees an average for the department, and then throw departments out according to whether the average of everyone in the department is kind of okay, or whether the average employee is in trouble health-wise. The second query says something quite different. It says, go to the IT department and select only the employees with blood pressure above 120. Go to the HR department and select only the employees with blood pressure above 120. Go to the CIO, CTO, whatever department, that level, select all the employees with a blood pressure of more than 120. And having gotten those, and only those employees from each department, compute an average. Obviously, this second query is going to show a number above 120 for every department, because for every department, it's going to get a bunch of numbers more than 120 and average them together. And so this is going to kind of get the people with blood pressure above 120 in each department and tell you whether of that group the average falls down closer to 120, like the people over the limit aren't that far over the limit, or whether the people who are over that limit are like way out over that limit. So yes, you can use a where clause when running an average or a sum or a count, but the where clause looks at the objects in the database, people or movies or whatever they are, selects only a subset to feed into the average function. The having clause, because it comes after the grouping and aggregate operation, instead looks at the results of running average and throws results out. Time to break? I just got asked an interesting question during the break. Is there any advantage or disadvantage when you do an order by to just naming the column number, column 1, column 2, or column 3 of your results, instead of just repeating literally the name or expression that you're using to compute that column? And the answer is it is more efficient to say order by and the number of the column, because then it doesn't have to compute the function over again. If you say order by 2, it will get the result set it's created and just use the value of the second column. Certainly in PostgreSQL, and I believe also in SQLite, if you say order by and repeat the name of the function or the addition or subtraction or whatever you're doing, it will actually run it a second time in case you're like computing a random number somewhere in there and it needs to be different every time you run it. So for efficiency, if you're doing order by or something like that, it's really helpful to name fields wherever you can instead of simply repeating the definition of the field. And again, another alternative to using the ugly little integers, which can really bite you if someone goes back to edit the query later and thinks, this would be much prettier if I put that field first, and forgets to go change the integers. That can't happen if you use the as keyword to give a cute little name to that result and then say order by that column, because someone who knows at all what they're doing, when they come in here to cut and paste and maybe they want these in a different order, they will know to cut and paste expression as something as a single unit, and would, in this case, if they decided that they wanted this sum or whatever displayed before the title, they would treat expression as name as a single column, which it is, so title would get moved here. And if you're really sleepy, this is something that you can mess up. You can select, oh, it's a big function. I want to also get the title, so I'll put it here. You've now really messed things up, because by like being tired and coffee deprived and myopic, you've looked and said, okay, well look, that's the thing I'm selecting. Let's also select title. And you missed the fact that, in fact, the full expression was really expensive function as a given name. And that this whole thing, really expensive function as and a nickname, that's the definition of the column that's coming back in the result. A second column, which, which can also have a nickname. Each column can have its own nickname attached, and if you're ever cutting and pasting or adding and removing the definitions of these columns that are coming back out of your select statement, it's important to always carry that as nickname with the formula or function, or you'll wind up with, values being swapped over to other names because you accidentally left the as foo stuck to the wrong value. So at this point, as we're now starting up our second half, I'm going to go into talking mode again for a minute, and I guess you've already detected that. And this question brings up the really important thing to think about, which is I said that SQL only knows about tables. It doesn't let you do all the cool stuff that a NoSQL solution would do of having little lists inside of things or objects inside of objects or structures like that. All SQL knows about is tables. You have to somehow manage to structure all of your data like this. Notice, now that you've had some fun playing with the select statement, notice that tables are also the only form in which SQL knows to reply to you. Tables are not only the sole canonical form in which your data can be stored on disk, tables are also what the result of every single select statement looks like. Let's see if I look backwards for that old title and year. This is a table. It's an on-the-fly, only exists for one moment table. Let me bring the select statement back. Every select statement creates an unnamed, anonymous, only exists for a second in RAM table, but it has all of the data properties of a normal table. It has columns. Each of the columns has a name, and each of the columns has a data type. It's a string or an integer, and you'll find you can't create a column of your select result that's either a string or an integer. It has to be one or the other, because what you're actually creating with select is a momentary, temporary table whose contents have been built by performing a query of some other tables. And so when we say that SQL is speaking tables all the way down to the bottom, we really mean it. It can only be talked to by your defining and building tables, and it can only talk back by returning tables to you. And so it's not accidental, but it's quite deliberate that the structure of the select statement, the structure of its return value, looks essentially, in concept, exactly like the definition of one of your tables, except that it's a table with no title. But it does have columns, and those columns do have names and data types associated with them. And when you use that little as statement, let me make this first a very small query so we can see it. And let's call this, hey, the title. You'll note that even though the first time I did it, the select statement, since I didn't use as, I didn't give it a pretty attractive title to use for these two fields, it just decided to use over again the name that they had in the original table. It said, well, he's selecting something called title. We'll just call it title. You'll note that if I do choose to include as, that it then ignores the expression that was used to build the value, and instead gives me back a table that uses the column name that I gave it. So when you use as next to all of the expressions that you're selecting, if you choose to do that, all you're doing is you're defining the column names in the synthetic, temporary, momentary table that's being constructed and then read back to you. Everything in SQL, everything it speaks about is one way or another a table. I should quickly mention indexing. You'll remember that I think one of the very first queries I did was maybe select all from movie, where title equals, and this is, I actually haven't seen it yet, but this is like one of the most famous movies in movie history. The called double indemnity. And notice that it takes kind of a moment to compute this result. Do you kind of see how the prompt takes a second to come back? Because, of course, what is it doing? Well, it's reading over the entire table, finding over and over and over again movies where the title is double indemnity, and it's spitting them back at me. This is going to be more clear if I say from role, where name is bystander. That's a much bigger table. How big is it? And, okay, let's see. It's about 5 million rows. And so it takes a little bit of time to scan the table and pull out all of those matches. You'll note that when we pull the movie Double Indemnity, that I've shown you so far how to play with matching, whether it's for video. I've shown you how to play with matching the title and whether it looks like or equals another string. I haven't yet really touched or played with this ID field. And the ID field is now, for the whole rest of our day, going to become key. It's going to become the thing that powers more complex queries and makes them work. It's going to become the thing that makes the ORM, the Object-Relational Mapper, SQL alchemy that we look at in a few minutes, work. And I want you to note that while selecting a movie by title kind of takes a moment to come back, and actually I think, are there, let's see, name is Connery Sean. Good. The actor table's larger, so this little pause before the answer comes back is very obvious here. What if I select this actor by ID instead of by name? How long did that take? Here, I'll try it again. Try to count 1 1,000, 2 1,000 until the prompt comes back. Didn't take long, did it? It's essentially instantaneous. But looking up by name is requiring more than a second. And obviously, as a table grew to millions and then tens of millions and hundreds of millions of rows, you want it behaving like this, where results come back instantaneously, because if your app is getting slower and slower and slower as people add more data, it's eventually just going to be so slow as to be unusable. The difference here is that if we look at the schema, the ID was declared not merely as being an integer. I mean, after all, year in movie is an integer, and it takes a second or two, as we've seen, to select movies by year. But the ID has been declared an integer primary key, and that does something very, very special. It tells the database that the ID must be unique. A primary key must be unique. There must not be 2 rows that have that same ID. Well, this puts the database in quite a quandary. How is it supposed to decide whether a new ID that you might try to insert, if you come along and say, here's a new row to add to the movie table, how's it supposed to know if that ID is unique or not, when there's probably millions or hundreds of thousands of IDs already in the table? What it does, in PostgreSQL and SQLite at least, is it, without asking you, without saying anything, it just makes an executive decision that when you declare something primary key, a field primary key, it's going to go add what's called an index to the database that lets you get to values in that field pretty much instantly. For those of you who know some computer science theory, an index is implemented typically on disk as a tree, very often as a B plus tree for those of you who are, or even one of the more advanced forms since the invention of the B tree and the B plus tree. But the idea is that it's sometimes a quite sizable region of the disk. I mean, indexes are not small things. It's a decision to add an index to your database because your database is now going to be bigger on disk than it otherwise would have been. But it's a tree that kind of says, all right, this is an alphabetic field. So the stuff that are like A's and B's go down the tree this direction. If the value you're looking for is like C, D, E, or F, go in that direction. And it kind of has a series of pointers to other blocks of the index on the disk, depending on where the number or string you're looking for lies in the alphabet. And then, if you go down to the CDE block of the B tree, it'll say, well, you know, if it starts with C, go over here. If it starts with D, go over here. And so as the database steps down through the tree, it's with every single step eliminating whole swaths of the alphabet and is very quickly arriving at the disk block that has the specific value and points over into the table on disk at where that row can be found. I should mention one thing that's very important for your imaginations. You might be thinking, why have this separate data structure called an index that lets me approach my data alphabetically or by numeric order, or however that particular index works? Why do that as a separate data structure when I could just keep the table in order on disk? Why not just have the movies by alphabetical order on the disk, and then I don't need an index? I just look at the middle movie, look at its name. Is the name I'm looking for before or after that in the alphabet? Step over and cut the remaining table in half. Go right to the middle element and say, well, is the guy I'm looking for before or after this movie name in the alphabet? And similarly, too, I said that in the index, each time it's a little choose-your-own-adventure story on the disk. Each time you step one block further into the index amongst all the choices it's giving you, you're throwing out huge numbers of choices and narrowing down very quickly on the little range of values or specific value that you're looking for. The same pattern would hold if we just kept the database on disk in order by title or name. So why don't we do that? Since we could start in the middle and have that same thing. Look in the middle, throw half of it out. Look in the middle of the remainder, throw half of it out, until we got down to the place in the alphabet where the specific name we were looking for lay, and then see if it was there or not. Or if the database went right from someone alphabetically before the name we were looking for to the one after without the name we're looking for even appearing. The answer is twofold. One, that would make adding data to the database extremely expensive. Because if someone started making a new movie, which happens from time to time. In fact, I started these examples with the Internet Movie Database, which is what I've downloaded to make this movie.db for us to play with. When I then, at the beginning of this week, just reran the import script to play with it again, there were new movies there that weren't 2 weeks ago when I grabbed it, because people keep making new movies. When they make a new movie, unless the name is like down at the end of the Z's, you're going to have to add it to the middle of the existing collection of movies somewhere, which would mean moving all of the data over, which by the time that gets to be tens of thousands or hundreds of thousands of movies is just not possible in a reasonable amount of time. Think of a database being used to store bank transactions. They can't move millions of database transactions over on the disk to add the fact that you've just bought something that began with the letter A. It's not feasible. The other reason we don't do it is that movies, though I kind of ran out of room here, movies have both a name, and I'll just stick it here. Maybe I could have fit it if I was more careful. Movies have both a name and a year. Well, which should we order them by on the disk? If we're going to be interested in looking up movies sometimes by year and sometimes by name, because, and again, Hollywood made it hard on us. They didn't come out with movies in alphabetical order. And that sounds very silly. Why would Hollywood have released all of the A movies in the 20s and then the ones starting with B? Batman would have been over by like 22 or something, 1922, and we wouldn't have any more of those. The only reason I mention that silly idea of Hollywood releasing movies in title order, I mention that because there are data sets that work like that. Sometimes you will have data sets where one or two of the columns are always ordered together because of whatever system or kind of data you're working with. So I don't want to rule that out, but in general, and SQL, if it's designed for anything, it is designed for the general case. In general, the names of movies are going to come in a different order for the year. So if you even tried the insane and not scalable approach of keeping the rows in order on the disk, you could only do that for one of them, because you would either be sorting them by year or sorting them by title, and whichever way you sorted them, you'd be throwing that other data out of order. And so they invented the idea of the index, this data structure that sits next to your table, because you can have as many indexes as you need. If we're interested in getting to movies by year sometimes, by name other times, you just create as many indexes as you need paths, efficient paths, into selecting your data. And therefore, the table didn't lose any generality when the database, seeing this primary key designation, decided that behind your back it would go ahead and create an index on ID so that lookups by ID are essentially instantaneous. Boom, 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 and we found or not found the ID that we're looking for. Because you can index as many columns as you want, you didn't lose any abilities you'd already have by the fact that it went ahead and created the first index on the table for you. And again, the reason that SQLite 3 does this when you designate a primary key is it just doesn't think it's reasonable when you try to add something with ID 500 to scan the whole table to make sure there's not already a 500 there. It goes ahead and creates an index to do that with. I will warn you that is not true of every database. Some databases, even if you want an index on your primary key, they make you do it. And if you don't, even just inserting your rows will get slower and slower and slower as you get to a few thousand rows. And then it just almost slows to nothing when you're trying to add your 10,000th row, your 10,001st row, because it's having to go every time back through all of the existing rows before it can permit you to add the next one. SQLite makes the decision to just throw in an index for primary keys. PostgreSQL makes exactly the same decision. If something is primary key, then there is already an index, and even if selecting by name is a little slow, selecting by ID, 305453, is essentially instantaneous. The way that we create indexes is through a statement very much like this. And I'm just going to call them I1, I2. Well, let's say, I'll call them, IDX, actor name. I might as well be somewhat semantic. You say create index, and just like you can name tables whatever you want, you just come up with a name that has, alphabetic characters and underscores. On table name, parenthesis, and then the name of the field that you want to index on. Note that this syntax is very similar to the create table declaration we've been looking at, where name of table, parenthesis, field. You do the same thing when creating an index, and the first time, when you run create index, it takes a moment, because it is now not only taking the time to read through the entire table, which it was doing every time I said where name equals Connery Sean, but it is going out to the side of the table on the disk and starting to write this big alphabetic tree that now will let us say, select all actors whose name is Sean Connery, and it comes back instantaneously. Because just as there was automatically an index on ID, we have now manually created an index on Connery Sean. I should note that indexes also speed up inequalities. Just like you can dive into an index going left and right to get to a particular value, you can also go in and find down at the bottom the index blocks that start at some value. You go in and find that, and then you can go in and find another value and select a range very efficiently the same way. So if we wanted to know everyone with, let's say, a last name of Connery, I can say select all from actor where name is greater than Connery, so Connery, comma, anything will qualify, and name is less than, and I guess, will it work if I say Connery, or actually just Connery A should come in alphabetical order after, I believe, all the Connery commas. Well, we'll find out in a moment, won't we? It worked! And notice how fast it ran. If I, and the opposite of create index is drop index, and here's where I wish I'd called it I1. What did I call it? IDX actor name. Oh, win for the live demo. If I drop the index and do this again, it takes quite some time because it just had to read the entire table in order to find the Connerys. It just had to manually, as it hit each row, test it against both conditions, just sort of like a fishnet, just dragging the fishnet through the whole pond and keeping the things that fit through the hole. It's only if we have, and here's our create index again, it's only if the index exists that we're able to do this quickly. And you might think that it's kind of really obnoxious performance-wise to have to go look at this index on disk. And in the one sense, it is. Having to look at anything on disk is just fatal to your application. Have any of you guys read Gustavo Duarte's, I don't remember the name of the paper at the moment, but he has this great analogy for understanding why disk access is terrible and fatal to your application. He says, let's imagine that a byte of information from the level 1 cache on the processor die, which is this little RAM chip that lives right next to your processor and can give it information really fast. Let's imagine that that's a word on a piece of paper on the table where you can kind of look and 3 seconds later you have your answer. Using that, level 1 cache equaling 3 seconds as a metric, and he wrote the paper in 2008, but those numbers are somewhat similar to today's. To look at the level 2 cache, which is a somewhat bigger memory cache on your motherboard or even these days on the die of the processor itself, hitting the level 2 cache then is going to take about 15 seconds. Maybe like grabbing a book from the bookshelf and opening it. Going to RAM to get the piece of information proportionally means leaving the room, walking down the hall to the coffee machine, getting some coffee, asking a coworker for the piece of the information, and coming back 2.5 minutes after you left the office. That's how expensive it is just to get to main RAM, your capacitor-powered RAM chips, which are kind of slow devices, compared to being able to pull the answer right out of the level 1 cache. in that analogy, having to wait for the disk head to seek to get a piece of information you need is the same as leaving the room, leaving the building, and wandering the earth for 1 year and 3 months before coming back with the sheet of information that you needed. Have you ever noticed your web browser comes up more slowly the first time, but then just starts almost instantly the second time? That's because the first time you run Google Chrome or Firefox, or one of its competitors, the first time, the operating system is actually having to move the disk head. Unless you're using a solid-state drive, it's like so steampunk. There's this actual arm in the computer that moves over to where the data is and has to wait for the spinning platter, which is only going 7,200 RPM. So the computer is sitting there waiting for months as the disk slowly spins, if you're thinking at computer speed, until finally the data it needs passes under the disk head and can be read in. So yes?
What is the difference between the greater than and less than syntax that we use with names like?
The difference is that SQLite 3 doesn't trust itself to use an index with like. I just created the index, so I'm going to repeat the question. The question was superb. The question is, why did I just do this incredibly bootleg thing of selecting star from actor and then why did I do this weird thing when I just want stuff that starts with Connery of saying, well, it has to be later in the alphabet than Connery nothing, but before Connery A. And the reason is this, and let's see if this happens like I think it will. I think that specifically with the bare bones little one single file SQL database we're using, that it gives you a syntax error if you, is that better? There, it's done. So did you see that it didn't, and the reason, apparently, is that like is a user-definable function that you might set to something different, which I think is the dumbest thing I have ever heard. Why would I want to, that's such a useful function. It's like SQLite. Can't we make a deal here? Can't I promise never, ever, ever to rename that, and you in return use the index? But I don't know the guy who wrote SQLite, and so if you want the index to be used, you actually have to apparently use a pair of inequalities. Yes, sir?
In your two statements, are you looking for something that is a little bit different between the like statement you just presented and
Yes, this,
here?
yeah, it's pretty different, because the like statement, come to think of it,
It will include a Connery A or a Connery B or a Connery C.
it would. It just so happens that no one has that name. If I wanted the like to be much more close to equivalent, I would have to remember to include that comma, because by putting the comma, and this is peculiar to this data set, the fact that it uses last name, comma, first name. But it just so happens that in this data set, by adding that comma, I'm making a query that's much closer in semantics to this.
But fundamentally, the data element you're working with is a comma delimited string. You don't necessarily have separate fields for first and last name.
Right. And of course, a fancier database would have separate fields for first and last name, et cetera. And I was just putting together a very simple example that would minimize the number of columns we had to keep in our head here today for our examples. Any other questions about that use of inequalities? And by the way, the answer to what I really do is I tend to use PostgreSQL, which as long as the like statement doesn't look like this, which an index isn't helpful with because this is allowed to start with anything. You don't know where in the alphabet it is. But with my favorite database, PostgreSQL, a like statement like this will just go ahead and use the index. but SQLite does not. I did not want to put you guys through the, let's say, the hassle of installing Postgres on your machine, since for many of you that would have been more difficult than installing SQLite 3. And so my examples had to be a little nerdy and use inequality to try to get a range of strings. Yes, sir?
Are there any other tricky inequality-like operators that can't use indexes?
It depends on the database in question. Whether you're using PostgreSQL, MySQL will have different rules than PostgreSQL. SQLite, and then all of their competitors will have different rules. So in general, I found that I have to kind of use consistently a single database to kind of learn its rules. Let me quickly consult the, well, that didn't help any. Let me come over here, and in another window, I'm consulting the time. And I'm having to convert. Right now, is it 11:41 or 10:40? What? 11:41. And 12:20 is the end of the tutorial? Okay. I just wanted to make sure that I, didn't keep taking endless questions on my little inequality trick if, say the state of your SQL education hangs in the balance, which it turns out it does. So, I'm now going to describe, and you have in your handout a number of exercises that involve it. But I'm not going to launch you into the exercises yet, but I'm going to, on the screen, do some things with an operation which is absolutely crucial, and will now show you why it is reasonable and why it works that we split data into such little pieces. The fact that movies are confined to one table, that roles are in another table, and that actors are in another, even though, again, going back to our MongoDB approach that I introduced earlier, we might have initially been tempted to just glob all of that information together into more complicated data structures if we had the opportunity. So it should be, I think it should be kind of, so we're now going to pay attention to the roles table, which we haven't looked at much. Again, when I'm exploring, I like to first ask the schema, ask for the schema of the table so I can see, all right, a role is a role in a particular movie whose ID we are given. A role is played by some actor whose ID we are given. And each role has a name, Batman. That is neither the role of the movie. Actually, in that case, it often is. Does not have to be, let's say, Gone with the Wind is the movie. Rex Butler is the name of the role, which is not the name of the movie, and it's also not the name of the actor. Roles have their own name that are independent of each, but in the way I've designed this table, they're deferring all other questions about the role to one of two other tables. It will give you literally the name of the role, because that's unique to each role, but they defer to this table kind of defers to the actors table, any further questions you might have about who played the role, and it defers to the movie table, any questions you might have about when the movie was made or what its title was. So if I select all from role, where name equals, since I ran, is it 1x or 2x's? Or is it even spelled anything like that? Huh? Red Butler? Thank you. I have now been exposed as someone who's never actually seen Gone with the Wind. Well, and this is one of those critical moments when I decide whether, so let me look at the queries I was planning to do. Select, well, no, I could. Well, it in particular will bring up every butler that's ever been in any movie. And do you have? Is it possible that they don't put commas? Oh, And so I can say select all from role or name like Rhett Butler. Let me go, and so if I do this query, and let's say I'm interested in this, just for fun, this first Rhett Butler. It should be obvious to you by now that if I want to ask questions about the movie that it was in, or the name, or the name of the actor that played it, I can just follow this up with a second select statement that says select all from movie where ID is this. That sounds suspiciously like a porn movie, which I was hoping to keep out of this. Let's do Gone with the Wind, 1939. I guessed that it just happened that these got inserted, I think, in the same order that the Internet Movie Database lists them. And good. So we have found now the movie that Rhett Butler played in, and going to the corresponding actor ID, selecting all from actor, where ID is this other ID, we see that it was played by Clark Gable. So you see that when you have a data definition like this, and where you use the ID, which is unique. It doesn't matter if several movies have the same name, the ID will be unique. It doesn't matter if several actors have the same name and gender, the ID will be unique. By having this magical row called, again, asking for our schema to be displayed, having a primary key that's just a random number created when, or in this case, a sequential number, but it's like a throwaway number created when the row is instantiated that's guaranteed to be unique. You have a way of referring to movies that utterly identifies them. Even if they have the same name in the same year, you know you've gotten to the right movie. You have a way of getting to actors that separates Michael Caine number one. Apparently there are other Michael Caines that the IMDb has given other Roman numerals to. You know you're getting to the right one if you use that ID. Because the ID is utterly unique, we're able to do queries like this one that gets Clark Gable and find out who uniquely played a particular role. This is what lets us avoid needing lists inside of objects inside of lists in order to create and describe relationships, because the relationships are implicit in the rows over in the other table that match the ID. Now, you've just seen that I can bounce back and forth between those worlds, like the role table and the actor table, by using IDs. So I looked for Rhett Butlers and found one in Gone with the Wind, played by Clark Gable. I stepped from the role table over into the actor table and looked at one of its roles. I can now step back the other way, and I can get all of the roles where ID is Clark Gable, 510, actor ID. Notice I'm only using the unqualified name ID in the table it belongs to, and then in other tables that refer to it, and this is a very common convention in the SQL world, but since column names are up to you, you can name them whatever you want, but the most common thing you'll see in tutorials and the way ORMs work is to expect this ID to be table name underscore ID. There are other possibilities, but that's the common one that I've followed here. If I select all rows where actor ID is this integer, then I get to see every role ever played by Clark Gable. I can even say, how many times has Clark Gable appeared in a movie? And I can wait, and I can find out that the answer is he was in 85 different movies in his career. If I see that he played himself in a movie with that ID, then I can select all from movie where ID is that. I can say, He was in a 1941 film, You Can't Fool a Camera. Maybe it was like interviews with different actors or even just a feature on Clark Gable, who is by then, I think, rather famous. But apparently he played in this movie as himself. And notice that I started with a role I was interested in. Because ID was indexed, I could bop right over to the actor. I could look up the roles they had played and then end by going over to the movie of a role I didn't even know about when I started. That procedure was a little too tedious for the people who invented relational databases. And so they invented a magical operator called join. Join is something you do right here in the select statement. Select, again, has the following structure. Select, comma-separated list of fields or values from, and so far we've only seen the form, from table where blah, 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 and then you qualify and describe how you want to limit and aggregate your result. But it turns out that instead of having to limit yourself to a single table, you can mash up several tables together in order to get your answer. So if we wanted to see all of the roles, let's see, how many movies have the name? Let's see. We'll do this. Let's say I wanted to see everyone who has ever played Batman in a movie with the title Batman. This is what SQL lets you do. And because I'm now going to have multiple tables over in my from statement, I now have to qualify names that I use in my list of expressions, in my list of columns for output that I'm creating, because actually title is unique, but name, which I'm about to use, could either be the actor's name or the role's name. So I'm going to grab the movie title and the actor name from movie, and I want to combine rows of the movie table with rows of with rows from the role table. Oh, well, which ones match? Well, I guess they match if the movie's ID equals the roles table movie underscore ID field. So I'll do this. I'll say get these two tables and munge them together, match rows from the two tables up if the movie's ID has the same name as the role's ID. And then I can join those munged up rows, because remember my question is, what were the actors' names who were in movies named Batman playing roles named Batman, by saying join actor, and in this case it's the thing that the way that a role knows it belongs to a particular actor is if the actor ID equals the ID from the actor table. So this select statement so far, if I hit enter, would be just a huge munged up table of every movie, every role of every actor ever. It'd be actually kind of fun to run it and run count on it to see how many roles have ever been played, period. But I don't want to take our time doing that. I'm going to actually ask the question I had, which is I'm interested in every row of everything ever played in any movie where movie title equals Batman and role name equals Batman. And my guess is that it won't complete because it'll take too long. And in fact, it won't complete because I forgot the word on right here. Again, if you go to the SQLite page and follow its little syntax diagram, it'll remind you that when you say join table name, it's on, and then a parenthesized comparison or condition. So let's try that again. And this actually might take too long to run. It didn't take too long to run, but it gave me no answer. Look for what? Hold on, let me stare at it for a second. Movie title, actor name from movie, join a role, where the IDs join actor, where the actor ID is the actor ID. Let's just, and it could be that I've messed up my, let's just try, is this, huh? Is that what I actually wrote up there earlier? Let me page up. No, I said role name equals Batman. And of course, it's taking forever, and that's what we're about to learn about next, is how indexes affect join. Let's change this. Let's do movie title, role name, actor name. And it's curious to me that, oh, frack! His real name isn't Batman! Oh. And actually, I'm going to give up on trying to match that part of it, because look at this. In the Michael Keaton Batman, he is called Batman / Bruce Wayne. And of course, that's up to the movie maker. I should have remembered that in doing like superhero movies, sometimes they're credited as the secret identity. Sometimes they're credited as the superhero. And then actually very often you see Superman / Clark Kent or whatever. So I'm going to immediately just go on to tackle another sticky question. And just for fun, I'll say, I'll make this work by saying role.name, and I'll just use Batman / and it could be that Michael Keaton is the only one that comes up. No, there have been 3 Batman movies. I wonder in what year that had a Batman. Notice how, and this very, very often happens, notice this process I'm going through. I did a simpler select statement. Okay, it looked kind of right. I did a more complicated select statement. It didn't work, so I played with it some until it was giving what I expected. Then I threw in even more data. Normally when I write a select statement, I do exactly this process you're seeing. I make it a little more complicated. Answer looks good. I do another join. And it doesn't work. And I have to poke around and very often ask to see the partial result without the where clause I just added to kind of figure out why things aren't matching up. But we now have a list of 3 people who have played Batman in 3 different movies. And we're creating a mashup of 3 different tables. Note that, again, the select statement is returning to us a table, because the only thing SQL understands is tables. And notice that the data in this synthetic momentary table that we're being returned is built from rows coming from several different places. The first 2 rows here are coming from the movie table part of the result, over there on the left. The middle one is coming from the role table, and the one on the right over here is coming from the actor table. And so we're kind of, again, in each of these getting what I'll call a mashup of data from 3 different tables, pulling together movies and roles and actors that match by that ID relationship between the actor ID and the ID field over in the actor table. And this is in fact how a real database guy will typically do queries that involve several different tables. Instead of the first procedure I showed you, where you look up the movie of interest and grab its ID. Then you go to the roles table and look up the things that match the ID, and then jump over to the actors table. A lot of database guys just prefer to do it in a single big query like this. You'll notice, of course, that this is running rather slowly. And I'll tell you, the reason is this. If we're in the role table, if we're starting there and trying to move over to look up a movie, happens instantaneously, right? Because the movie ID here is an indexed field in our movie table, and so the movie can be looked up immediately. Similarly, the actor ID here is an indexed field when we jump over to here, and so it gets looked up immediately. But the problem is that if we're not starting with a role and going somewhere else, like in the query I did, we're starting kind of with the movie title, then if we find the movies that match and go to the role, this isn't at the moment an indexed field. There's no way to start with a movie named Sleuth, grab this ID, and immediately get to see the matching roles because we haven't indexed those fields. Similarly, if the database wanted to start with the actor, grab its ID, and just leap right into the role table to the matching rows, it couldn't do it. So I'm going to, and I won't try to give them interesting names this time, I'm going to create two indexes which in fact permit that. They're both going to be on the role table because it's at the moment our problem child that has these nice ID fields that uniquely identify other objects but that aren't indexed. And I'm going to say create an index on role actor ID, and I'm going to put a semicolon to complete the statement. Sorry that all of you have probably had to discover that on your own since I didn't mention it until now, but yes, all SQL expressions end with a semicolon. And
Quick question.
yeah.
When you get to that situation, let's say you made a mistake, and you get that, how do you get out of that?
I entered a semicolon on the second line and hit
No,
enter.
Let's pretend there's another error, and have you ever got that where you
I think-
say you spelled from incorrectly and you hit enter and it just gives you that eclipse in the thing? How do you get out of that to get back to correct your statement?
The eclipse in the thing.
The eclipses, that's the three dots. I actually,
Control C is often how I do it, but I think.
I have to control D to get out of it.
Okay, and that might depend on what operating system are you using? Okay, and that might depend on how Mac OS handles interrupt characters, though.
I kept putting within my phone.
Huh. Yeah, hitting Control D actually closes the entire program for me. So it depends on your operating system and how the terminal control characters are set up and interpreted. So we're now done with that index. I'm going to create an index on the other. And before I do that, I should note, when you get confused about this and you're wondering why a query is taking a long time, this varies slightly with the database, but it works fine in PostgreSQL and MySQL. Use your arrow keys or whatever to back up to the query that took a long time. Or if a program you're using is issuing the query, as we'll see in a moment with an ORM, you can do something called, it's just called explain in PostgreSQL, but I believe is called explain query plan. This is a somewhat less standardized part of SQL, but you can ask your database using explain one way or the other to explain how it's going into the data to try to find the answer. So we can see here that it's scanning the entire table movie. And then it's using if we did this query right at this moment, it would use the index we just created to do that instantaneous jump from movie to role, and then make another index because it says using integer primary key to jump over to the actor. Does that mean? I always want to write indexes, but in SQLite it's indices. I don't have an index, do I, on movie name? So notice this query plan that it gave me pointed out a problem. Scan the entire movie table? I know to begin with I want the movie's name Batman. Oh, I don't have an index on Batman. There's no way to find the Batmans without either reading the whole table or creating an index on movie where I say title say again? Oh, we'll call it I2 so I can type it in a hurry if I want to drop it later to make an example of it. Now if I say explain query suddenly every step it will take for every result row is apparently an indexed step, looking up the movie by title, jumping over to the role by title, jumping over to actor by index, jumping over to the actor by index. And therefore, all of those should be fast. All right, watch for the prompt at the bottom to see how long it takes. Well, I didn't expect it to take that long. How about you? Search table using index, using index. Any ideas? I could try. The explain query plan, search table movie, and by the way, I am in my day job a PostgreSQL person, so I must admit I am often a bit perplexed by SQLite 3's decisions when doing queries. Did it take this long the first time, or have I actually managed to create an index that has slowed SQLite 3 down? Let me try one trick. Hey, Control-C worked. So if the query is running, I can Control-C it. That was what I was remembering. On mine, for some reason, if I've started the statement, Control-C doesn't do anything to get me out of it.
When you get locked into that, you forgot
Yeah.
to put in a SQL statement.
I always forget to do something, and actually I don't always forget to do it. I did it, I believe, for the copy of the database you guys are using. But, whether it helps here or not, I'm going to ask SQLite, very often when it tries to plan its queries, a database needs to kind of know what values are common in what tables. Because and this is something kind of cool that SQLite doesn't do very well, but listen to what PostgreSQL will do. Let's imagine that I was using ranges. I was looking for actors whose names all start with Smith, and I was looking for movies that were all in maybe the 19-teens, or maybe in the whole 19th century. Notice that depending on what values I chose for the exact same query, it could be more efficient to come in from one direction or the other. Because if I choose a last name like Smith that's very common, it's going to have to choose a humongous number of Smiths. Go to every single row they've ever played. Go to every single movie that those roles were in to find maybe just the movies that were in 1910 and 1911, if that's the way I'm selecting movie years. It would be much more efficient to start with those few movies in 1910 and 1911, pull all of the roles that were in them, and then just look through all of those results for actors whose name was Smith. On the other hand, if the only change I make to that query is to make the last name very unique, it might select only one actor and only have to look through his 30 roles to find matching movies. If I make the movie range suddenly the whole 20th century, because a friend has asked about a 20th century movie with such and such a criteria, suddenly that could, as compared to when I'm just looking for 1920 and 21 or something, if I expand it out to all movies, then the coming in from the direction of the year of the movie could be a very bad choice because it could return a huge number of movies, every one of whose role you have to look up, to then go look up every one of those actors to see if they have the name Smith or an even more unique last name. And just the values you choose in your inequalities can make it worth it for the database to come in from the other direction. This ability of a relational database to choose whether to use the indexes over kind of on the right of the tables and to come in from the actor to the role to the movie, or whether to come in from the movie and then go to the role and then grab the matching actors, or whether to start with the roles that match if you have any criteria that limit the number of roles, and then to go in each of the tables that it indexes. The ability for the database to make that decision is the genius of SQL. if you wrote this using a procedural language, if you just sat down with Python and could only look at one table at a time, you would have to decide whether to loop over movies, and for each of those, loop over the roles, and for each of those, try to go grab the matching actor. Or you'd have to write it the other way around, where you started with the actors. And the problem is that the most efficient direction to come in from, the most efficient way to use the indexes that are present, can change not only between one query and another that have different forms, but even two nearly identical queries, one that says Smith and one that has a very unique last name, could change the way that it's most efficient to perform the query. This means that if you write a web page or a form in a business application that lets someone select some years of a movie and a last name and shows them all of the actors that have played in movies in those years, you can't write a single loop that will always perform efficiently, because they could put in all of the years that movies have been made or just one. They could put in a horrendously common last name or a very unique one. And depending on the value they stick into your little field forms, you can wind up, if you've written those loops by hand, having a query that literally takes 10 or 20 minutes, or in some cases, years to complete, in cases of where databases have billions of rows, like a bank database that has all the transactions that Walmart has ever undertaken at a store, or something like that. Depending on whether you go in from one direction or the other, can literally mean the difference between a query that takes milliseconds and a query that takes years. And the genius of the SQL language, the reason that it was invented, is the select statement simply describes the way you want data combined without committing to what indexes you use or what order you hit the tables in. Only by leaving that vague and hazy and just describing the outcome that you'd like to see can a database like SQLite kind of say, well, this index exists but not this one, so I'll come in from a different direction. And only that allows a database like PostgreSQL, when you've run analyze, to actually say, oh, he's asking about a very uncommon year. Let's do that first. Or, I don't think that last name is one of the more common ones. Because when you run analyze in SQLite 3, it just gathers some basic statistics. But like a big industrial database like Oracle or like PostgreSQL, which is kind of the open source Oracle, it's just crazy. The 30 years of research that database researchers have done in finding more and more clever ways to pull statistics from what this has done. It's just done a single scan all the way through each table and built some like normal distributions and stuff like that of how the data is, or figured out the distribution of data in the table. And thanks to doing that, SQLite has some kind of simplistic algorithms. Something like PostgreSQL has insane algorithms that will find really, really complex and useful ways to pull data together. They'll even do things like, if you do this kind of join we're looking at that combines all three tables, they will realize that the join is probably going to select such a large number of roles that you're going to hit maybe 50% of the table anyway. So what they'll do is they'll run your limitation on like movie years and actor names first, generating two like Python dictionaries essentially of IDs of matching movies and IDs of matching actors. Then they will make one pass over the role table looking to see if the movie ID is in that dictionary in memory and if the actor ID is in that dictionary in memory. Because if you're going to have to hit half the role rows that are in your database, which would happen if you wanted to do a query, like let's say over all movies that weren't straight to video or something like that, it's actually less efficient. Imagine a table. Imagine we need half of the rows in it. It's actually very inefficient to come in through an index because the index will keep sending you to the same disk blocks over and over. As you slowly go through the index that has all of the data in some order, you'll be hitting a particular disk block, which typically has several dozen rows on it. You know, you'll be hitting, if Michael Caine and Laurence Olivier happen to live on the same disk block, you'll hit it both when you hit Olivier in the alphabet and when you hit Caine in the alphabet. And instead of reading in the table once in order to get half of it, you'll have done the equivalent of like reading the table 100 times, because you'll have hit each block so many times for each row that's in it. PostgreSQL knows all that, and it will do like insane in-memory dictionary-based joins of huge chunks of data pulled off the disk if it figures out that using an index naively would send it into the same data so many times over again. This is really the genius and the magic of SQL, is it defers until query time the decision which can destroy your performance of which direction you come into your data from. We have a few minutes, so let me now cover the one or two more topics. First, I should mention transactions. This is a huge topic of its own. Okay. First, I should mention that the way, and sorry that is this kind of readable even though the font is smaller? Who can't read it? Oh, drat. If I go into my PyCon SQL tutorial and bring up a second SQLite on movie.db, the way that, so there are, I'll let you go look up their syntax, but there are statements like insert, update, and delete that let you add a new row to the database, or, and this is scary, update and delete let you add set values in or remove an unlimited number of rows, because in update and delete, you build a select criteria with all the where clauses to limit the update that you do. So usually you just say, update the row where ID equals 5. Update this row where ID equals 10. I will conservatively estimate that 99% of the SQL queries that have occurred in the world from when I began this talk to now have been of the form update, set these values, where, and then a where clause that just selects my bank record to set it, or a transaction to set the amount of money on it. But it is possible to write an update that goes into all of the roles matching Michael Caine and does something to them. It is possible to write an update if you don't have a where clause that hits every row in your database, because that's what select does if you select with no where clause, right? So to remove everything from a database is just don't hit enter, don't hit enter. I won't even hit semicolon. That will drop every row in the movie table because it has no where clause specifying what movies I want to remove. I'm now going to use the insert statement to illustrate this. Select all from movie where name is foo. Movies have titles, not names. There are no movies ever that have been named foo. If any of you are computer scientists, this will appall you. Let's say, and so the next thing I want to mention, that there's this thing called transactions where I can begin is the keyword that starts a transaction. I can say insert into movie, title, year, and again, this syntax you can just look up in the SQLite documentation. But let's say that this year, which is 2012, we're going to come out with a movie named Foo. If I go over here and rerun my select, it still sees nothing. If I come up, oh, that's curious. Select all from movie where title is Foo. And this prompt, looking at the same database, can see the data when this cannot. The reason is that I've begun a transaction but haven't committed it yet. The two options you have, having run begin, are to either roll back and other clients never, ever see the data you entered, or if I can begin again, and now this is showing it, if I instead end with a commit, you saw it took a moment, committing always takes a second, but now all other clients connected to the database can see what I did. Why is this useful? Because often in banks and places like that, you need to go update several values in several tables to bring the data into full consistency before it's safe to let all the other clients see what you've done. Typically, to prevent hacking and people trying to game the database, a bank needs to move money out of my account and into your account sort of simultaneously, where no one else connected sees one of those having happened without the other, because then the balances don't add up in the bank's database. So transactions are really useful if you're designing systems where several tables need to be touched, and then it's safe for the other connected clients to see that series of changes that you've made, and they'll see it as just an instantaneous. There's a moment in time where they can't see any change you've made in the transaction, and then there's suddenly a moment where they can see every change. And the guarantee of the database is that there are no moments that are not all or nothing. Thank you. I will skip temporary tables and simply show you a piece of code. Of course, what many of you came here to do is to, I've tried to show you how SQLite exists as a standalone language, what it looks like when you use it standalone, what's really behind any system that uses SQL. And I will finish by showing you two pieces of code that show the two main ways of using it from Python. In one, which is to use something, an interface called the DB API, and all of the different Python libraries that either let you talk to Postgres or that let you talk to something like SQLite tend to follow, all offer an interface that looks like this, where you create a connection, you set up, you actually have to grab something called a cursor that lets you look, that's what feeds back to you information from a table. And then what you do is you say .execute, and you have a SQL statement right in quote marks in the middle of your Python code. I tend to use double quotes so that I can then use single quotes inside, which you'll remember is what SQL likes. And also, it tends, these DB API libraries will do string interpolation for you. Notice here, instead of like trying to use a %s and then do my own string interpolation, notice that here I'm leaving it, and I used the wrong quote mark. Here, I'm, instead of using a dot format or % to format this string myself, I'm letting the database layer, this DB API layer, stick the title in here for me, because what if the title itself has quotes in it? That could create a SQL expression that in the most famous instances drops tables from your database. If you've ever seen the XKCD cartoon where a family name their son, where his name ends in quote, semicolon, drop table students. And if you do your own interpolation, SQL doesn't know that the quote that comes in from your title is different than any other quote, so it thinks the string just ended. Only by letting the database layer do your quoting will it put backslashes in front of all the quotes so that they look to SQL like part of the string, not like part of your SQL statement you're trying to write. Having done an execute, you do normal Python stuff like loops, and then you can treat the rows as dictionaries to loop through your data. And a lot of people find this horribly ugly. Do you guys know that like when you start as a Python programmer, you use dictionaries for everything. And then you finally get really sick of having to say a movie bracket quote title all the time, and so you decide to learn about objects so that you can say movie dot title. And that is why they invented ORMs, the most famous one for Python being SQL Alchemy at the moment, really powerful, really nice, and what it lets you do for the exact same thing we just saw is say I want to is you define objects for each of your tables in a little language it has that looks a lot like a table definition. Here, for example, is the actor table, an ID, a name, and a gender. It's a normal Python class, so I was able here to give it a wrapper that makes it pretty when you print it out. But what you can do once you've explained to SQL Alchemy that movies should really be backed by, or let's say, I guess we go up to movie, that movie should be backed by the table named movie, you can then do a series of the exact same operations that you saw select can do. Filter by adds a where clause, order by adds an order by clause. If you look at the SQL Alchemy docs, it has a little way to add to your query, piece by piece, all of the expressions that you will have wanted to add to your select statement. And when it runs it, what you get back are objects like movie that has it's not a dictionary with a title key, it's actually an object with a dot title and a dot year. And the fun is that if you change them and then tell SQL Alchemy you're done by telling it to commit changes you've made, it will write the correct update statements to go make those changes in the database that you made to the object. So SQL Alchemy is really powerful for talking about individual objects. If you want to go and set something on every row in the database, just write an update statement. But SQL Alchemy is really cool because normally in an application, you're showing a user a movie on this web page or in this printout. And SQL Alchemy can be a really convenient way to write code that looks more Pythonic, that looks like it's talking about a movie with a title, that doesn't look like it's playing with a bunch of dictionaries and then substituting values from them into a bunch of complicated select statements. It does selects for you automatically when you query. It does updates or inserts automatically when you're ready for one of your models to be saved. Finally, do go look up the ability of SQL Alchemy. You might think that if you're talking about individual objects, that SQL Alchemy is going to be limited to just select the guy with this ID. Okay, select the guy with that ID. Okay, select all of the roles that have this movie ID. Okay, select the actor with that ID. And that your performance is going to be killed as you look at a movie and all of its roles and all of its actors in Python, you can just talk about one object at a time, and you might think you're going to be killed by all these individual transactions. SQL Alchemy gives you a way out by letting you actually do joins right in your query so that instead of doing select, 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 select to pull all 50 actors that might have been in a film, it does the same kind of join that I showed you before and pulls it with a single query. So I hope, obviously this is a huge amount of material, but I hope that, especially by the time that I gave you to play with select, to build up some queries and to get a little experience with it, I hope that you now have enough of a picture of what the database is doing for you that whether you call the database manually with SQL statements from your code or whether you're in a position, either that you got into or someone else put you in, where the queries are being written by an intermediate layer, you now understand that the database is good when you give it a big join where it can figure things out. Database is a lot less efficient if you just ask it for one little piece of data after the other and it can't see the big relationship you're trying to pull together with your loops. And I hope that you've enjoyed seeing what I think is a really cool language that lets the computer do things it's good at that no other language permits. Thank you very much. And let me make a final caveat. Because so many of you, thank you guys, by the way, for answering my emails about where you're at. Because so many of you had never touched SQL before, you can kind of tell I weighted the class towards sort of the ABCs of the select statement, because that's where you've got to start, this ability to get the table stored in the database and pull out a new little table with just the answer to a particular question. So we spent half the class on that because I wanted to let people who've never even done that before start with those baby steps. For those of you who already knew about select and are like, darn it, I thought he would talk for 3 hours about nitpicking awesome details about SQL alchemy. I am willing to meet with any of you guys later to talk more about that. You guys paid to be here. Take my email address. I will put it here in a comment. I don't come do tutorials so that I can talk about SQL for 3 hours and then wash my hands of it and not care whether you guys succeed when you go back to your jobs or your hobbies and try to get some of this to work. I do it because I love this technology, because I love people who are really good at what they do and make all of us look more awesome by all the problems we're solving for our employers and other people in the world. And if there's some point I didn't hit well enough, just something I didn't cover, ask me in person at the conference, email me later. If the way I explain select just didn't work for you, ask me to come help, because the point of this is for you guys to be able a little bit to start using a new skill in real life. So don't be afraid to contact me later. Thanks.